8.1, in the first half, we're going to be taking the derivative of exponential functions. So it says here, the natural base e is the most convenient base for exponential functions. One reason for this claim is that the natural exponent function e to the power of x is its own derivative. So if I were to take the derivative of e to the power of x, that gives us e to the power of x. Now, if we have more than just x going on in our exponent, we have to multiply by the derivative of whatever our exponent is. So technically the derivative, because we're not just going to have e to the power of x, there's going to be more going on in our exponent. So e to the power of whatever is in our exponent is e to the power of the same exponent. We keep it exactly the same and then multiply it by the derivative of the exponent. So if I had something like e to the power of 2 times x, when I take the derivative of this, let's call it the derivative, we keep it the same, so e to the power of 2x, and then we multiply it by the derivative of the exponent. What's the derivative of 2x? 2. So this would be 2 times e to the power of 2x. So in example 1, we're going to find the derivative of e to the power of 3x minus 1. We can use substitution here to help us. We can say u is 3x minus 1. And the derivative of u, if you want to call it u prime or du, doesn't matter. The derivative of u would be what? 3. Perfect. So when we take our derivative, we'll call it f prime. So our derivative would be the same. It's e to the power of u times u prime, or the derivative of u. So here, our derivative would be e to the power of 3x minus 1 times the derivative of u, which we said was 3. So to write this a little bit neater, we would just call it 3e to the power of 3x minus 1. And that would be our derivative. So you don't really have to use substitution here. Sometimes using the u's makes it just a little bit more confusing. Some people like it because it makes it a little bit more organized. Whatever you want to do, just don't forget to multiply it by the derivative of the exponent. U's come a little bit more handy when we are taking the integral, which we'll do tomorrow. Let's look at example 2. So for our derivative, we're going to keep it exactly the same. So e to the power of negative 2 over x. And then we multiply it by the derivative of our exponent. So what is the derivative of negative 2 over x? So be careful. How would I take the derivative here? What would I need to do to make it not a fraction? So we'd make it negative 2 times x to the power of what? Negative 1. Now when we take the derivative, we'd multiply our exponent by our coefficient. So we would get 2 times x to the power of, we subtract 1, negative 2. So this is 2 over x squared. So this would be our derivative of our exponent. This is, we'll call it du or u prime. So we're going to multiply it by the derivative of our exponent, which we said is 2 over x squared. So to write this a little bit neater, we can say 2 e to the power of negative 2 over x squared. We could move the e to the bottom too, just because it has a negative exponent. But we could leave it up top. Either way is fine. Example 3 says find the relative extrema of our function. So this is incorporating what we did in chapter 5, I think it was. So To find our relative extrema, we're looking to see if we have a relative max or min, so we need to do the first derivative test. So first thing we need to do is take the first derivative. Here, I've got two terms. I have x and e to the power of x that are being multiplied together. How do you think I would take the derivative here? What's the rule that we have? Perfect, the product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. So our first term is x times the derivative of the second. What's the derivative of e to the power of x? Yep, same thing, e to the power of x. Plus the second, which is e to the power of x, times the derivative of the first. What's the derivative of x? 1. So this would be our derivative. To find our relative extrema, we need to find our critical numbers. So we would set this equal to 0. So set it equal to 0 to find the critical numbers. So to solve, we could take out our GCF. Let's pull out an e to the power of x, and we're left with x plus 1. Set them both equal to 0. So now this ties in what we did with chapter 7. How would I solve e to the power of x equals 0? What would we do? Take the ln of both sides. Can I take the ln of 0? No. So this does not give us an answer. It does not give us a critical number. So you can't take the ln of 0. But I can solve my other one here. I'm going to subtract 1 on both sides. So x is equal to negative 1. So my critical number is negative 1. So I'm going to make my little chart over here. Negative 1 is my critical number. That would go in the middle. My left interval that I have would be from negative infinity to negative 1, and my right interval would be from negative 1 to infinity. So to find our relative extrema, we need to see where we either go from increasing to decreasing or decreasing to increasing. So we need to find where we have a change in our slope. So I need to plug this into our first derivative to do our first derivative test to see if it's increasing or decreasing. So when we plug it into our first derivative, we could plug in anything from negative infinity to negative 1. What would you want to plug in? Negative 2. Good choice. So if we plug in negative 2, I'm plugging it into my derivative here so I can plug it into the simplified one. So f prime of negative 2 would be e to the power of negative 2 times negative 2 plus 1. Let's think about it. What is e to the power of negative 2? Is it going to be positive or negative? What does a negative exponent do to our number? It makes it a fraction. And e is 2.7 something. It's a positive number, so it's turning our positive number into a fraction. So is it going to be positive or negative? It's going to be positive. This is going to be positive because it's just making it 1 over e squared, and e squared is e is 2.7, so when we square that, it would just be another number, but it's just a positive number. We only care about the sign of it. It doesn't matter what the value is. Then we have negative 2 plus 1. Is that going to be positive or negative? It's going to be negative. So if we have a positive number times a negative, what are we going to get? A negative. So we end up with a negative number. Does that mean that this is increasing or decreasing? Decreasing. So this is less than 0 because it's negative. We are going to be decreasing. Next, let's test our other interval from negative 1 to infinity. What could we plug in here? 0. Great option. So we're going to plug in 0. We have f prime of 0. We're plugging it into the first derivative. When I plug in 0, we have e to the power of 0 times 0 plus 1. What is e to the power of 0? 1, which is positive. And then 0 plus 1 would be 1, which is also positive. So f prime of 0 is going to be positive. So are we increasing or decreasing? Increasing, since we're positive here. So if we go from decreasing to then increasing, at -1, are we going to have a relative maximum or minimum? A relative minimum. Awesome. So we have a relative minimum at the point -1, comma, how would I find my y? Plug it into the original. Awesome. We're going to plug it into our original function. So to find the y, we just plug it into f of x. We're finding f of -1 here. So we're going to plug -1 into our original function. -1 times e to the power of -1. Let's simplify this a little bit. What did we say that a negative exponent does? Makes it a fraction. So it'd be -1 over e to the power of 1, which would just be e. So -1 over e.
So what do we do with the capacity? Or we just keep it in terms of...
Yeah, just keep it in terms of e. So this would be our relative minimum. So example 4 says find the points of inflection of the standard normal probability density function here. How would we find the points of inflection? What do? We find the second derivative, and we find where our second derivative is equal to 0. That would give us the points of inflection. So for our function here, it looks intimidating, but 1 over the square root of 2 pi, this is just a coefficient. It's just the value out front. So our x is only in the exponent here. We don't have to use the product rule or anything because we just are dealing with a coefficient. It's an ugly coefficient, but it's just going to hang out front along for the ride. So let's find our derivative. I'm going to leave 1 over the square root of 2 pi out front. And then let's take the derivative of e to the power of -x squared over 2. So our derivative of e to the power of -x squared over 2, we're going to keep it the same, e to the power of -x squared over 2, and then multiply it by the derivative of the exponent. So our derivative of our exponent is -x squared over 2. What would our derivative be here? -x, perfect. We'd multiply the 2 out front, cancel out with the 1/2 that we have, and then subtract 1 from the exponent. So -x. So to rewrite this, we could say -x over square root of 2 pi times e to the power of -x squared over 2. So this is our first derivative. What would we have to do to find the second derivative? We would find the derivative of this, but how? What rule would we have to use here? If we've got an x in our first term here, and we've got an x here, what's happening between them? We have to use the product rule. So we're going to use our product rule. So that is the first times the derivative of the second plus the second times the derivative of the first. So the first would be negative x over square root 2 pi times the derivative of the second. So the derivative of e to the power of negative x squared over 2, we're going to keep it the same, e to the power of negative x squared over 2, and then multiply by the derivative of the exponent. What's the derivative of negative x squared over 2? Didn't we just do that? Negative x. So that is the first times the derivative of the second plus the second, e to the power of negative x squared over 2 times the derivative of the first. What's our derivative of negative x over square root 2 pi? It would just be whatever our coefficient is, so it'd be negative 1 over square root 2 pi. So let's do some simplifying. I can combine the x's in my first term here. What's negative x times negative x? X squared, perfect. So we've got x squared over square root 2 pi times e to the power of negative x squared over 2 plus e to the power of negative x squared over 2 times negative 1. I'm going to make this a minus here. Just pull the negative out front and leave it positive 1 over square root 2 pi. So this is our second derivative. We could write this a little bit neater. Do we have any GCFs that we could take out? So I've got one term here and one term here. What do we have in common in both of those? Awesome. E to the power of negative x squared over 2. So I can take that out. Anything else? Awesome. 1 over square root 2 pi. That is also in common in both of them. We could write this a little bit better and put the e on top, but we'll just leave it like this for now. After we take out our GCF, what do we have left? Just x squared? Minus 1, perfect. So this would be our second derivative now. So to find our inflection points, we would want to set it equal to 0. So we set the second derivative equal to 0 to find the inflection points. We're going to do the second derivative test. So we can set e to the power of negative x squared over 2 over square root 2 pi equal to 0 and x squared minus 1 equal to 0. When we solve the first one, I can multiply both sides by the square root of 2 pi, which would just stay 0. So we have e to the power of negative x squared over 2 equals 0. Then what would we do to solve for e? We take the ln of both sides. Can I take the ln of 0? No. So this one does not give us an inflection point. Let's solve our other little equation here. We have x squared equals 1. Take the square root. So what does x equal? Plus or minus 1. Perfect. So we've got two values here that we need to test. So I've got negative 1 and positive 1. We have negative infinity to negative 1 and negative 1 to 1 and 1 to infinity. What am I plugging in when I test my values? What am I going to plug the values into to see where my inflection changes. Do we plug it into the first derivative or the second derivative? Second derivative. Perfect. So we're doing the second derivative test to see where our inflection is going to change. So what's a value that we can plug in between negative infinity and negative 1? Negative 2. So we're plugging that into our second derivative. We plug in negative 2 into our e part here. So for f, the second derivative of negative 2, when we plug it into the first part, we end up with a positive number. When we square negative 2, we would get negative 4 over 2, which would be negative 2. The negative exponent would move e to the bottom, which is still going to be positive. When I plug in negative 2 into the second part, negative 2 squared would be 4, minus 1 would be 3. So this would also be positive. So positive times a positive would be positive. So we're dealing with a positive number here. For our second derivative test, we're talking about concavity. So we have a concave up part here. Because this is greater than 0, it's positive, we are concave up. Let's test a number in our second interval. What's a good number we can plug in here? 0, perfect number. So when we plug this into our second derivative, when I plug in 0 into the first one, it's still going to be positive to our first term here. When we plug in 0 into our second term here, 0 squared would be 0, minus 1 is going to be negative. So positive times a negative would be negative. So we're dealing with a negative. We are less than 0. Negative, we are concave down. So it looks like a sad face here. And then let's test our third interval. We can plug in 2. We end up with a positive and a positive, so this would be positive. So when we plug that into the second derivative, we are positive, so greater than 0. So we're concave up. So because our concavity changes, both of these values are our inflection points. So we'd have an inflection point at negative 1 and positive 1. How do we find the y values? Plug it into the original equation, perfect. So we'd find f of negative 1 and f of positive 1 here.